Hello everyone, my name is Ved Prakash. My roll number is 2511AI58. Today I and my teammates Sanidhya, Jeel and Teeth, we will explain about Monte Carlo tree search algorithm. In this video, we will explain about background and why we use the Monte Carlo tree search algorithm. We will explain the full working algorithm and then we will demonstrate you some of the good examples and then applications, improvements and the limitations of this algorithm. What is Monte Carlo tree search? Monte Carlo tree search MCTS is decision making algorithm used for the complex problems. It searches very large decision space using simulations. It represents problems as a tree of states and actions. It estimates best actions using statistical results from the simulations and widely used in the game AI planning, robotics, and optimization problems. To understand why MCTS is important, let us first think about how computers play games like chess or Go. In these games, every move creates a new possible game state. If we represent all possible moves and the future outcomes, we get something called game tree. At the top of the tree is the current board position. From this position, many possible moves are available, and each of these moves leads us to another set of possible moves, and so on. Very quickly, this tree becomes extremely large. For example, for the chess, the number of possible game sequences in the chess is estimated to be around 10 to the power 120. And similarly for the Go, even it is extremely large for the Go. Because of this enormous search space, the computers cannot analyze every possible future moves. In this slide, we are showing how the decision tree is formed. For example, here at the start, we have current board position. We can have current board position of the game. And these are the possible moves we can have at this board position. And from these possible moves, we have to select the best possible move, which will lead us to a win or a best outcomes. Additionally, game playing AI used algorithms like min-max combined with the alpha-beta pruning. The basic idea of the min-max algorithm is that it tries to simulate the future moves, assuming both players are playing optimally. It explores the game tree to a certain depth and then uses a evaluation function to estimate how good each position is. Alpha beta pruning improves this process by eliminating some of the branches that cannot influence the final decision, allowing the algorithm to search deeper. These techniques works very well for the games like chess. However, they face some of the major challenges. First, the game tree can grow so large that even with the pruning, it becomes impossible to explore the enough of the branches of the tree. Second problem can be these algorithms relies heavily on the evaluation function, which are sometimes very challenging to craft for problems having large branching factor. For example, Go and AlphaGo, these games are very large game space tree. So for these, it is very difficult to craft a evaluation function. Designing a good evaluation function requires a deep expert knowledge about the game. And in the complex games like Go and strategic patterns are extremely complicated, making it very difficult to design the accurate evaluation function. Monte Carlo tree search algorithm takes a very different approach. Instead of trying and analyze the entire tree or manually design the evaluation function, MCTS relies on the simulation and the statistics. The idea is very simple and very powerful. From the current game state, the algorithm repeatedly simulates many possible games by making random and semi-random moves until the game ends. Each simulation produces a result, win or loss or maybe draw. By repeating this process many times, algorithm gathers a statistical evidence about which moves tends to lead to better outcomes. Over time, the algorithm focuses more and more on the moves that appears promising and ignores the moves that performs poorly. In this way, MCTS can efficiently explore a very large search space without needing a complex evaluation function. Monte Carlo tree search algorithm works in a four main phases: selection, expansion, simulation, and backpropagation. In the selection phase, we select a move from the current board position. From the current board position, we have multiple possible moves. We select a move and expand that move fully to the leaf node and try to get the UCT values, upper confidence bound for the tree node. Uh, on the basis of that value, we decide uh, how much promising this move is to reach us to the win position. Uh, Based on this UCT value, upper confidence bound value, uh, we explore and exploit our moves uh, in the game tree. And more number of simulation we perform, more will be the accuracy of our UCT values will be. And we will explore the less promising less promising number of moves, less promising moves, and we will exploit the more promising moves again and again during the process. In this way, this algorithm works. More will be explained by my teammates.
Hi everyone, my name is Sanidhya and now I will explain you Monte Carlo tree search algorithm. So, the algorithm begin by initializing the root node, which represents the current state of the problem or game. After initialization, the algorithm repeatedly performs four major steps: the selection phase, the expansion phase, the simulation phase, and the back propagation phase. During each iteration, the algorithm explores the search tree, performs simulations, and updates statistical informations. These steps continue until the computation exceeds or the time limit it reached. So finally, the algorithm select the best action based on the collected simulation statistic. So, so in this slide shows the complete workflow of the Monte Carlo tree search algorithm. The process starts with the initialization of the root node, in which we initialize two variables. The first one is q, which is equal to 0, and n, which is also equal to 0. Then the algorithm repeatedly performs the four phases: the selection phase, the expansion phase, the simulation phase, and the back propagation phase. After the back propagation phase, the algorithm checks whether the computation limit is reached or not. If the limit has not been reached, the process repeat again, starting from the selection phase. And if we reached, then we finally the computation limit is reached, then the algorithm select the best move of the collected statistic data. So, so in this selection phase, the algorithm start from the root node and move down to the search tree. Then we traverse the tree until we reach the leaf node. At each steps, it select the most promising child node based on the previously collected statistics. This continue until I reach the leaf node. The decision of which node is to select is made using the UCT formula, upper confidence bound formula, which balance exploration and exploitation. The main purpose is to balance the exploration and exploitation, is to select the best child among them. So now the UCT formula, upper confidence bound for trees, So the formula is UCT of SA is equal to Q of SA plus C into the square root of natural log NS divided by NSA. Here QSA stand for average reward of action. The N represents the number of the visited to the state. The NSA represents the number of times an action was selected. The C is the exploration constant. So finally, this formula helps the algorithm decide which node should be explored next. So the next phase is expansion phase. In the expansion phase, if the selected node has unexplored actions, the search tree is expanded. A new child node is added then, representing a new possible action. This node represents the next state. The search tree gradually grows with each iteration, and that's how the expansion phase works. So, in continuation, the next phase is the simulation phase. It is also known as the rollout. The algorithm performs a random simulation from a newly expanded node. The simulation continues until a terminal state is reached, such as win situation, loss situation, or a draw situation. I am taking an example of the chess game, which is also you will learn in the next slides, upcoming slides. So the result of this simulation provide an estimate of how good that move is. And by taking these estimates, we will add them and get the best result out of them. So after doing this, we reach the last phase, the back propagation phase. In this state, the simulation has finished its work. The algorithm performed the back propagation part. The result of the simulation is propagated back through all visited nodes. Each node updates its statistics, including visit count and the reward value. By this, we are going to check whether we got the best move or not in the final move selection. After repeating the 4 phases many times, the algorithm select the final move, the best move. Argument max is equal to n. We choose the action with the highest visit count. This means the algorithm chooses the action that has been visited the most times during the search process. Thank you.
Hello everyone, my name is Jil Patel. My roll number is 2511AI12. Okay, till here we cover how Monte Carlo algorithm works and why we use Monte Carlo algorithm over such traditional searching algorithm, which is explained by way. Okay, now let us understand Monte Carlo tree search using some simple examples. Okay, suppose an AI agent is playing a game, and the problem for AI agent to decide which move will lead us to the best outcome. Okay, uh, in traditional method, we analyze every possible future move in the game tree, which can be extremely large. Okay, but Monte Carlo algorithm uses stimulation. What is stimulation? Which is explained by Sanitya very well. Okay, the algorithm starts from each possible move and stimulate many random games until the game finish. Okay, each stimulation gives us a result as win, loss, or draw. In our case, we consider loss or draw as the same. So we have only two possibility: either win or either loss or draw. By repeating this process 100 or 1000 times, the algorithm collect statistical information about which moves perform better. This slide shows us the fully tree representation of our game. Here blue node shows us the current game position. Till here we explore everything in our game, and green nodes is a future possible moves such as v1, v2, and v3. Okay, out of these three moves we have to select one move so that we can get best possible outcome in future. Okay, here
NV1 shows that number of times we select move V1, and QV1 shows that out of NV1 times how many times we win in the game. Okay, this slide shows us the stimulation result. Okay, for all three moves we stimulate them 1000 times. Okay, out of 1650 times we shows that V1 wins, out of 1420 times we shows that V2 wins, and out of 1500 times we shows that V3. Now we interpret the results. Okay, move V1 has the highest win percentage. Okay, this suggests move V1 leads to the better outcome. This algorithm therefore select move V1 as the best decision. With more stimulation, the accuracy of this decision improves. Okay, this slide is a tree representation of very famous game Tic-Tac-Toe. Okay, root. This is the current board position of our game. We have to place X now, and we have three possible ways. Okay, first one is we can put X here, second one we can put X here, and third one we can put X here. Okay, now at the beginning we have UCT value for the all the moves is same, which is 1. Okay, now what is UCT? Upper confidence bound for tree. Here WI shows that how many times we win after selecting this move. SI shows that how many times we select this move. SP is the number of time we select the node of among three of this parent node. SI is same for here, and C is here exploration coefficient. Okay, which is we consider always as a root 2. So at beginning we have the UCT value for all three moves is same, so we select any move randomly. So we select this move, okay, and after this move we have same for UCT value among their childs. Okay, so we consider this, out of 500 times we select this move, out of 500 200 times we select this this position for O, and 300 times this position of O, and we stimulate this positions till the game ends, and we know that these moves gives us the win. Okay, after getting this win we have to backtrack and update the values of the here and here also. Okay, and for how we explore in this formula. Okay, now as we explore the 500 times this, the number of SP is increasing. As the number of SP is increasing, our UTC value for this move also increase. Okay, so this will lead us to say explore this move and this move also. After some number of the stimulation we explore these moves and 200 moves also, but exploring 200 moves which will lead us to the not getting win. Okay, so we explore this move less number of times, we show in this formula also. Okay, okay, now I will explain the very famous application of Monte Carlo research, which is AlphaGo. AlphaGo was developed by DeepMind to play board game Go, okay, which is known to be extremely complex because it has huge number of possible board positions. Okay, AlphaGo combines MCTS with the deep neural networks. This neural network predict the promising moves. Okay, MCTS explore variation of this move. This combination allowed AlphaGo to defeat the world champion player. Okay. Okay, this slide shows the algorithm of Monte Carlo, okay, along with the deep neural networks. Okay, here there are mainly two neural network used. The first is policy neural network, which looks at the current board position and predict the most promising move instead of checking all the possible moves, so that it suggests the best few moves to explore. Okay, and the second is value network, which evaluate the board position and predict which player is more likely to win. Okay, this prediction helps Monte Carlo tree search run simulation more efficiently and choose the best move. Okay, using this approach AlphaGo defeat the world champion Lee Sedol in 2016, which was a major through in artificial intelligence. Thank you.
So from this slide, I will be explaining you. My name is Patel Tirth and my roll number is 2511 AI07. Real world application of Monte Carlo research. It is used for a board game like a Go, chess, because these games have an extremely large search space, meaning there is a too many possibilities move to check one by one. And Monte Carlo helps to simulating many possible future movements or selecting the most promising moves. Second is a poker-like game. Third is a general game like playing a AI system. This system AI designed to play a many different type of game without being specialized programmed for each one. Fifth, next one is robotic playing or navigation system. Final is optimizing and scheduling problem. For optimizing and scheduling problem like planning, task, logistic or resource allocation where many possible decisions exist and the best one we will choose efficiently. Next slide is about Okay, this slide is about Monte Carlo research with neural network, policy and value. So initially we have a current state or a game or a problem. This state is passed to a policy network. The policy network is predict which moves are most promising and it is example a network suggests like a move A, B or C. Here we are taking a directly A moves because it is a more prominent moves. Instead of exploring the every possible moves, we are directly choose the highly probability moves. After that, we are going to the value network. Value network is estimate the probability of winning from that position. So here we are giving a P of winning. So in this diagram, we want to explain about the policy network and value network for the neural networks. So policy network suggests the promising moves and value network estimate how good that position. Slide is about the limitations of Monte Carlo research. As we know about from the example, here require many simulations many possibilities, even a millions of sometime even thousands possibilities. Second problem is the large decision space. The search tree become extremely large. This make algorithms slower and more memory intensive. After the third is a random simulation may produce the noisy result. Means sometimes because of this, sometimes simulations may give a misleading outcomes. And real-time system computation time is limited. Like whenever we are working about the robotics or a fast decision-making environment, this may not be enough time to run many simulations. This can limit the performance of Monte Carlo in time-critical applications. In this slide, we are talking about the improvements for Monte Carlo tree. So, to overcome these limitations, researchers have proposed several improvements to Monte Carlo research. First, we can design the better simulation strategy. Instead of completely random simulations, smarter simulations policies can produce more accurate results. Second thing is the Monte Carlo can be improved by the integrating machine learning models such as neural networks. This model help to guide a search toward the better decisions. Third thing is a parallel processing to run simulations faster. What it means? It means by running simulations multiple CPUs or GPUs at the same time, we can significantly speed up the algorithm. And the finally, hybrid algorithms combining search and learning. So modern AI system use the hybrid algorithms. Like we are using the system like a ChatGPT or this, like using a hybrid algorithms, which combine the traditional search method with machine learning techniques. And this combination allows system to learn from the experience while still exploring the possible decision moves. So by these four strategy, we can improve our Monte Carlo research. Okay, thank you guys.